Okay, so we will continue with the discussion on LSR, least square regression. Towards the end of yesterday's class, we looked at the classical problem of fully developed turbulent flow in a pipe, where the dimensionless heat transfer, which is given by the Nusselt number, can be written as A Reynolds number to the power of m and Prandtl number to the power of n. Suppose you are considering experiments over water or any other fluid. If the fluid is fixed, the Prandtl number is fixed. So A into Prandtl number to the power of n gets fixed for the problem under question. So you can put it as C Reynolds number to the power of m. But so far we have learnt only linear regression, that is y equal to ax plus b. So this is basically what is called as a power law form. Something goes as a Reynolds number to the power of something. So it is possible to take natural log on both sides and reduce it to the form y is equal to ax plus b, and I gave some typical data. I gave results of a hypothetical experiment which we conducted by varying the velocity and then determining the heat transfer rate, and then from the heat transfer rate we get the heat transfer coefficient, then we converted it to Nusselt number using thermal conductivity and all those stuff, and then I gave 5 representative values, Reynolds number varying from 2500 to 18,000, and the Nusselt number is appropriately varying. I started with Reynolds number 2500 because Reynolds number 2300 is the limit for transition turbulence for a pipe flow. Right, now let's work out this. I will give you 10 minutes. I will start filling it out. Don't look at the board, you do it yourself and independently check whether you are also getting the same thing, right. So the log will be is it okay? Just check this. Is it all right? What is the sigma of, what is sigma x? 44.1. Good, 44.1. So what is x bar? I don't know whether x bar is required or not. We'll just calculate and keep it. Huh? No. Huh?
8.83.
8.83. Okay, keep it. Of course, this can be done using Excel. You can use it. You do it on various software. You can write a program and all that. But this is the first time you are doing regression. If it is the first time you are doing regression, it is important to do hand calculation. Hand calculation is the best way. Even when we teach finite element to students, we ask them to take 2 elements and do hand calculation first. You should know what is going on in the computer. Okay. So if you look at this, (55) is 4.01, is it? 00. Okay, 01. You are able to see Vikram? Or you want to come here? Sum is 19.97, all right. Yeah, please check, please don't copy from the board. I am not solving a very tough partial differential equation which you cannot follow. I am just doing simple math. Senthil, what is the mean? Y bar? (3.9944), right? 3.994. Now the more tedious operations come. You have to get x squared, 7.82 square. This is 68.72. $88.17. $96.00. So the x square is 392.36. Okay, from this side, Jimin, Vikram, tell me, are you getting these values? You are able to see the board? Akshay, what are you doing? SMS?
0.788.
Huh?
Just give an example.
Huh? Minus 3.1.
You can discuss at 9:50. What exam was that? Oh, this was the postponed. What was that? Linear algebra. What did you learn in linear? What are you learning? Huh? Matrix inversion.
So it's actually a mechanical course, fundamentals of engineering design.
We are studying linear.
But prof is teaching enough.
So stiffness matrix and all.
Differentiation of tensors, then
Tensor, huh? Oh.
Divergence of two words.
Divergence of stress tensor. Vector itself is difficult. Huh? So, second order tensor, there are many second order tensors. There is a book on continuum mechanics by Prager. But of course, as engineers, if you want to do advanced studies on mechanics, you need tensors. Basically, a notation, it helps us to. The notation scares people, that is a thing. Okay, so xy. So patience is required. If you want to do linear, if you want to do regression and all that, you cannot make mistakes. Do it slowly. Okay, it's not like a puzzle or whatever. It's mostly a test of your rigor. Whether without mistakes you can do. It's not very high funda and all that. If you are systematic, it's very simple and straightforward, right? So what is the? We require xy 178.39. I think we now have enough. Now we have all the quantities required to calculate A and B. Please go ahead and calculate A and B and declare that that is a best fit that represents the Nusselt number as a function of the Reynolds number. So y bar was 3 point. I am simply writing that y bar in all the columns. Okay, so A is equal to okay. What is 6 to the power of 0.4?
2.05.
6 to the power of 0.4 is 2.04. So what I have essentially done is I have conducted some hypothetical experiments. I started out with the relation which I am already aware of, namely the Dittus-Boelter equation. Okay, so it is 0.023 Reynolds number to the power of 0.8 into Prandtl number to the power of 0.4. I assume that the fluid is water. So 6 to the power of 0.4 is 2. 0.023 gets multiplied by 2. I am getting 0.4604. So I start with 0.4604 Reynolds number to the power of 0.8, and I will just write these values, and then I will smear these values with some error. This is how we prof generate problems. Okay. We do not take from textbooks. Okay, so it is pretty straightforward. It is also physical. No, you know that if you conduct a heat transfer experiment, if it is carefully done, you will get a result like this. You will get a result that is worth knowing. Okay, so I put 2 more columns. Why did I do that? To find the goodness of the fit or the absence of it, whatever, right. So now I want to do y fit. I want to calculate y fit. In order to calculate y fit, what I will do is, for each data point I will substitute the value of Reynolds number, raise it to the power of 0.801, multiply by 0.0464 and write out this column. Can you do that? So this Reynolds number to the power of 0.8 is very typical of turbulent flows. It is wrong. I do not get you.
Not substitute in that equation. We have a and b directly, we can put y equal to x plus b.
No, there are 2 ways now. There are whether you want to check directly on this equation, or you want to directly check on this. There is a dilemma there. Where do you want to check? You want to check out this, then I will erase this. Huh? Are you getting the point? So there is a confusion as to whether you have to check on the ln or the actual performance on this. Okay. So if the class feels that we should not check on this ln, and because, why are you giving a blank face?
Since you are regressing on the logarithmic value, should we be checking the fit on the logarithmic?
Okay, the debate starts. Whether we should be checking on the logarithmic values or ultimately on the Nusselt number itself.
Because the regression is a linear regression in the log term.
So in my notes I have done it based on the Reynolds, based on this. In the class I wanted to do this, but whatever you want to do, we will do now. You have to decide. Whether, huh? Huh? Whatever on the regression, then we'll do this. Yeah. Now let's complete the other 2 columns. I hope others got the point. Since it was A Reynolds, C Reynolds number to the power of m, we did some ln and reduced it. Whether we should test it on the ln of something or on the actual this thing, that is the doubt. Somebody can check it out whether there is some difference between the 2. So y fit, please get the y fit. Deepak, can you tell me? No, now we will say that what will be the regressed values of y according to that equation. No, this y is this ln of nu. Okay, so ln nu. Take 0.064464 to Reynolds number to the power of 0.8, then take ln of that. What are you getting? You will get values 2, 3, 4, 5, 6 something. What is the first value? 3.06. Okay, next.
3.98. 4.4. 4.41.
4.41.
4.7.
4.73.
Okay, so that's fine. Oh, now there is a pain. So this also we need a log of this to calculate this. Okay, y minus y bar whole square.
0.65.
0.65.
0.17.
0.17.
17.
17.
ये ना बहुत कम है थर्ड वाला
4 into 10 to the power 6, then
0.62.
0.6, okay. Now sigma, why are we finding y minus y bar square? Good question, I am going to answer all these questions. Okay.
0.65.
1.65. Yeah, do the y minus y fit. I think it will help if you have one more column. What is that? Y.
Yeah, that's a decimal that much.
Deepak, just give me the values. Ln 24. We already have, no? Okay. Yeah, this is just to help you. Yeah.
3.6 10 power minus 4.
3.6?
10 power minus 4. 2.3 10 power minus 3. 3.2 10 power minus 4. 2.9 10 power minus 4. 1.7 10 power minus 3.
1.7.
Yes, sir.
Sigma. Yeah, in the exam also you have to draw so many rows, huh? But anyway, you guys finish it in 15 minutes. It will take about, to calculate everything, it will take about 20 to 30 minutes if you know the procedure. Is it okay, Vikram? Yeah, sigma is how much?
0.05.
Point?
0.05.
0.05? Okay. All right. Is everybody through with it? Soumya, you got it? Huh? Okay. So, I call this as ST, total, I mean, S is the sum of the residue, the sum of the residue with respect to the mean, and sum of the residue with respect to the fit is SR. Okay. Now I can define I can introduce a term called R squared equal to ST minus SR divided by ST. Calculate that. This R squared is called the coefficient of determination. The root of R squared, which is R, is called the correlation coefficient. You get an obscenely high value. What is it? 98. 98 is all right. Am I endlessly introducing more and more quantities and what is all this, what is going on? Okay, there may be a genuine concern. Now if you are done with this, then I will I will put the Funday now. Is everybody through with this? Okay. So we are able to get the values of A and B, we are able to find out y minus y bar, y minus y fit, we are able to determine some statistical quantities and something is close to 1, so you believe that it is good and all that. Now I am going to tell you what is going on behind the whole thing. Okay. How was this please put down your pens, and if you have completed just listen to this. Now we did some heat transfer experiments, we varied the Reynolds number and got the Nusselt number, and we believe that the Nusselt number and the Reynolds number are related by a power law form like this, and then we went ahead and did a regression or a least square regression, and finally we got some values. Has it really helped or not? We require some statistical measures. Suppose I did not have any heat transfer knowledge, what I had was only the Reynolds number versus the Nusselt number. So what I will do as the first step is basically look at the Nusselt number y and then get the mean. Okay, then I will tell the outside world I do not know any functional relationship, but the mean value is likely to be like that. You can get a mean of, in this case if you take ln of this, what is the mean? You are likely to get a ln of the Nusselt number as 3.9944. But do you stop with the mean of the ln of the Nusselt number? You do not stop with that. You say that if I say that the mean is like this, the mean is expected to have a variance which is like this. Every data point will have y minus y bar which is like this. Therefore the total residuals which is given by the difference between the log of the Nusselt number minus the log of the Nusselt number average, if you sum all that it will come to 1.65. However, if I get smart and I say that instead of saying that I will qualify only by the mean, but I put y is equal to ax plus b, as it helps, now I am saying that with respect to the fit I am able to reduce the ST from 1.65 to 0.005. So out of 1.65, 1.60 of the 1.65 is already explained by the fact that Nusselt number goes as A Reynolds number to the power of m. Therefore 97% of the variance in the data is explained by this correlation. Therefore it is a good correlation, okay. So that is a story. In the absence of a correlation you will report only the mean and the standard deviation, but apart from the mean and standard deviation you go deeper and then find out some physics behind this and then propose a line, and you are able to explain much of the variance in the data with this, then and your R squared is very high, that means you have a good correlation to work with. Are you getting this point? So that is the whole thing about the coefficient of determination and the correlation coefficient. All right.
Get plus or minus 0.98.
Yeah. So that plus or minus 0.8 could be, some books will call minus 1 is also all right. That is, it is when x is increasing, y is decreasing. It is basically like that.
That is 2 times 0.98. All the data points lies between.
No. That is not the. Here we say that 97% of the variance, 97% of the variance in the data is explained by this correlation. Suppose you have a correlation which gives only 60%, either your experiments are erroneous or there are additional variables which you have not taken into account. So when you do a regression it will tell you so many things. It is just not your experiments or the simulation which will help you understand the subject. When you do a regression it will tell you so many things, which are the points which require to be repeated and so on. So that minus is basically sometimes it when x increases y decreases and so on. Alright. Apart from this we also can draw what is called a parity plot. So if you have something like this, so let us say this is 10 and 10 or something, you should have points like this. This is called the 45-degree line. when you write your project reports or when you do research, when you write a research article, there is also another way of graphically depicting the relationship between the y data and the y fit using this way. So the points must be equally spread on both sides of the 45-degree line. This 45-degree line is called the parity line. This whole thing is called the parity plot, this is called the parity line. If all the points lie on this parity line, it is incredible. That means it doctored data. If you do any experiment, you will have a natural variation, because if you will measure a voltage, you will measure flow rate, you will measure temperature and so on, there will be natural variability. So point should be on approximately 50% of the point should be above the line, 50% of the point should be below the line, and it should not be smeared. That is, there is lot of scatter here, means there is some higher order physics, that is when the Nusselt number is increasing, when I get more error, there are some second order effects, there are additional variables like effect of variation of viscosity or some other parameter which you have not taken into account. That is very important. So you can draw a 10% plot like this, you will draw like this, you say this is plus 10%, minus 10%, whatever, it looks to this thing, but you can draw what is called bands. This is another way of presenting the results. So this is called a scatterogram. Scatter plot, or it is also called a scatterogram. I can do additional things. So I can on the same parity plot, I can have red color, green color, blue color to denote fluids of different Prandtl numbers. So it is all, I mean, beyond a certain point, it is just creativity, how you present the results, how you plot and so on. Alright. Now, what is the funda behind this whole thing? Can I wipe it off? Yeah.
Y fit is the fitted the results, assume some relation and you got y fit.
Yeah.
So when you are finding y, that SR okay, if it's small then it's basically a good fit.
Correct.
So, but how small it is, we need some other measure to compare it to.
No, that's R square.
You're using ST.
Yes.
So I just want to know why ST is a good measure of.
No, in the absence of anything, only mean and standard mean. For example, in this classroom, I want to find, suppose I want to get the height of a particular student in this class or whatever. I want a measure of this. I measure the heights of all of you, okay, and then I take an average. Then I say that it is the average height is likely to be this, but then that SR will come, that is a variance. Of course, Surekha has to be left out. Surekha and Mridula have to be left out. They are not a part of this model. They have to be in separate model, because boys and girls there may be some variability. Okay. So what I am saying is, in this, so the first step would be, I can take the average of, I can take all the data points, take the average, and then I can find out the difference of the individual height from this and report that with plus or minus 3 sigma 8, and if the class is large, it is likely to follow a Gaussian or a normal distribution. Now I say that I want to fit a correlation. Now I say we can go one step further. Suppose I know the date of birth of each of this fellow, and now I say that the height is directly proportional to the date of birth of this fellow. That is y is equal to ax plus b. With the date of birth, I am getting a much better fit than taking all this thing put in Excel and taking the average height. Now if you tell me the date of birth, I am in a much better position to give you the height. Is that clear? So what is the reference? Whether the date, with the date of birth I am getting something good or not, that benchmarking is without the date of birth, with just raw analysis of the data with respect to a crude mean, how it performs. Okay, relationship with yeah.
Why did we have to draw a horizontal line? We could have drawn we knew that as R increases, Y increases, then couldn't we have chosen a better benchmark, like drawn a line?
No, if you already start thinking, then you are regressing. basic point in data analysis, nothing else is known, you will start with the mean and standard deviation. You will try to plot, you will try to draw a histogram, then if it is a large sample it will follow the Gaussian model. If you already started thinking about something, then you are already started regression. Okay. So the relationship with probability. Now let us talk about 4 points. Okay, so we want to draw some straight line through this. So this is our LSR fit. For example, now assuming that all the measurements are made with the same instrument, I can assume that the errors associated with the measurement follow a Gaussian with the same standard deviation sigma. Okay. Now for x1 so for purposes of illustration I have taken only 4 points. Now assuming that the distribution of errors is Gaussian, and I am saying that y equal to ax plus b, this is basically y fit, y fit is equal to ax plus b, the probability of getting y1 for this particular set AB to be true, AB are the 2 parameters which are yet to be retrieved, is given by, is that correct or y1 correct. This comes from Gaussian distribution, normal distribution. Similarly, the probability of getting y2 for the same given AB is given by so therefore the probability of getting y1, y2, y3 and so on for a given AB is just given by the product of all the probabilities, right. The probability of getting y1 multiplied with the probability of, we cannot add, the probabilities have to multiply because these are what are called IIDs, right. You learnt about all this. These are all independent samples. I mean, there is no connection between the first and the second. These are truly independent events. If this were to be so, then this total probability can be given by L. L is given by now you turn around and find the best values of A and B which will maximize P, correct. You want to find out those values of A and B which will give the maximum probability. This in statistics, if you solve this equation to get the if you want to solve this equation for the maximum values of P, you are essentially doing what is called the maximum likelihood estimation, okay. So you can actually do minus 2 ln L or minus ln L. If you do minus ln L, what do you get? You do 2 n plus this is also there 2 sigma square. Sigma is not a variable in the problem, right? Sigma is known, it is an instrument characteristic. Now you can go ahead and call this as P. You can do dou P by dou A is equal to 0. So, in the last class we started with just this. So, we should have started from here. So, there is a link between what you have done and probability according to this basically comes from what is called the Gauss-Markov theorem and all that. Okay. So, there is a relationship between the probability as defined by the Gaussian distribution and okay. So, these are basically maximum likelihood estimates, correct. If you solve for this you will get A and B. So, this is the connection between what we did yesterday. Somebody had a doubt, I told them I promised him that Deepak or somebody had a doubt, I promised that I will bring out the connection between these two. Is this clear? Let us not get into this too much, so it is fine. Now let us solve one more problem, that is the problem number 17. Let us do some unsteady mercury in glass thermometer in a patient's mouth. I am looking at an example which is analogous to this. How does the temperature respond? The doctor keeps.
Yes, sir. Exponential.
Oh. When will it reach the core temperature of the human body? Infinite time. So what is infinity for the doctor? 2 minutes. 2 minutes you will get 99% of the information, because the mercury in glass thermometer is so designed that the time constant is very small. A thermometer kept in the armpit will take 5 minutes, it will take 5 minutes. But however, if you drink Pepsi and go to the doctor, then it will show incorrect reading, or if you drink coffee then you will be admitted. Okay. So half an hour before and after you should not take all this. Therefore, these are all so yet it has to be treated with caution. So in Europe they use ear temperature, they have a thermometer where it just touches the eardrum, or in even India now we get something which measures the forehead temperature, or like the swine flu detection you will have a thermal infrared camera and then okay, but that is AK-47 to kill a mosquito, right. So that is a normal clinical thermometer. Doctor will even at the end of 1 minute he will have a good idea how it responds. Okay, 2 minutes he will have a fairly good, because this 98.6 is not you are not going to have 98.6 throughout 24 hours, you know that, right. The human body has the lowest temperature at about 4 am and has the highest temperature at 3 pm in the afternoon or so. There is a diurnal variation of plus or minus 1 degree Fahrenheit, okay, 0.5 degrees centigrade. After food it goes up, after exercise it goes up, when you sleep it goes down. Okay. So early morning if the temperature is normal, it may still be fever, because that is why fevers will become very clear in the evening. When already the body is hot, then over and above this normal temperature it will be 99, then any fever of 1 or 1.5 will show us 100.5 or 101. So So fevers tend to increase, you feel it is increasing because already there is a component loaded to it, right. So the 98.6 degrees is the average body temperature of a British male who is not having fever. Now no longer people no longer accept it, 98.6 is not, nobody care, doctors will not care, anything less than 100 they will not worry. If it exceeds 100 in the morning time, morning if it exceeds 100 then you are in trouble. If it is 99 and all that, nowadays nobody gives medicine, okay, but it is, so it's part of the variation. Okay, now what is the story about this? It cannot go down, no? Now if m is the mass of the system, the first order system, Cp of course in this case it will be plus Ha theta because the temperature is increasing. I am writing this equation for a system where theta decreases with temperature, that is a cooling. I can say theta temperature excess is given by T minus T infinity. I can now say MCP so this is basically called the lumped capacitance approach method. So at time t equal to 0 this will be theta I, okay. So this tau equal to MCP by HA. What are the units of tau?
Seconds.
You are sure? Second inverse?
Second.
Okay. Time constant. Now is it a heat transfer class? No, it is an optimization class, so we are doing regression. Why am I teaching you this? I am teaching you the background so that we can work out a problem. So basically if you conduct unsteady heat transfer experiments, okay, if you know theta I, then you will get theta as a function of t. You can get some experimental points like this, okay. It is possible to treat this as a system, first order system with two unknowns, theta I and tau, okay. And now you can solve for theta I and tau. From tau, if you know what is the mass of the system, if you know the specific heat, if you know the surface area, and if you are pretty sure that the heat transfer coefficient is not changing during that narrow interval, so this gives you one more method of evaluating the heat transfer coefficient using an experiment using unsteady heat transfer. Because if you have to do steady heat transfer, you have to repeatedly carry out several experiments, okay. Now why do you want to treat this theta A also as unknown? Because the moment it starts there is a rapid decrease in temperature, therefore this theta I may be prone to error. It is good for you to treat theta I as an unknown, find out theta I and compare with the experimental values which you already obtained. So this is a standard way of getting heat transfer coefficient using unsteady experiments. Now I can make it a little more interesting. Suppose I can have a dome like this, I can have a foil, I can have vacuum, I can heat it, and if this is the MCP A, everything of the foil is known. So here I can measure the temperature, this is vacuum. Now I completely avoid convection. Now the temperature response will be like this, the temperature of this will go up in time, but now the governing equation is Therefore, if I carefully do experiments, if I get temperature as a function of time, I can get the emissivity of the surface. This is pretty interesting. dt by t to the power of minus t infinity to the power of 4 in partial fractions 1 by t square minus t infinity square minus 1 by t square plus t infinity square into 1 by 2 infinity t infinity square, that can be further broken down into 1 by 1 minus t minus t infinity 1 by 1 minus t infinity tan inverse of plus log of all analytical solution is possible. This should be asked in quiz, okay. You can reduce it using partial fractions, okay. So this is a standard way of getting emissivity, but you require a vacuum. Are you getting this point? So in the exam, I don't know, depending on my mood, I will give some readings for emissivity or the forward. This is called the forward model. If you solve this, this is basically called the forward model. This becomes easier, but if I have a problem like this, it becomes more difficult and more involved for you to get the solution. So in the next class, I will again come up with some problem where something is cooling. I will give you some data, but now since it is e to the power of minus t by tau, if you have to take ln, and then it, just like today you did ln of Re, ln of Ru, we will do that and complete this, and then we will go to multiple linear regression, where I will show it on the Microsoft Excel because it will take a long time for you to do in the class, and then we will round off our discussion with by taking a very realistic and very powerful case of nonlinear regression, where this for example theta I and tau or epsilon, for example if it varies with iterations, then it is going to be a lot more difficult, okay.